Good afternoon, everyone. Welcome to today's session organized by Institute of Corrosion India branch. Today's topic is Impressed Current Cathodic Protection of Steel in Reinforced Concrete. We have with us Dr. Arpit Goyal. Dr. Goyal is a corrosion and concrete durability specialist with extensive experience in research, academia, and industry. He holds a PhD and postdoc from Coventry University, UK, where he developed a patented concrete conductive anode paint for impressed current cathodic protection of reinforced concrete structure. He currently serves as General Manager, Cathodic Protection Group at Structural Specialist and Projects India Private Limited, and he is the chair of the Institute of Corrosion India branch. Dr. Goyal has authored more than 25 peer reviewed journal papers, several book chapters, and over 15 international conference papers in reputed forums. His research interest spanned corrosion mitigation of reinforced concrete, sustainable and smart cementitious material, and innovative electrochemical rehabilitation system for infrastructural durability. So, without any further delay, I'll hand over to Dr. Arpit Goel.
Thank you, Shabista, for the introduction. So today it's, I will be talking about compressor and cathode protection system. Last month in September, I think we had a lecture by Dr. Tarade who we majorly discussed upon corrosion of reinforced concrete structures. He covers various aspects of its fundamentals and some protection techniques. Today, I'll talk about a subject that's becoming increasingly vital in terms of durability of concrete structure, that is impressed current cathode protection system. So ICCP is a proven and internationally accepted technique for controlling corrosion in reinforced concrete structures. It has been successfully implemented in decades in bridges, jetties, tunnels, car parks across Europe, Middle East, UK, US. However, in India, I feel the cathode protection is still established in oil and gas industries and pipeline industries. But if we talk about concrete structures, its adoption is still very limited. In my point of view, it could be probably due to lack of awareness, limited design expertise, and shortage of trained professionals. So through this presentation, I will try to cover some basic fundamentals of impressed current systems, what kind of anodes we are available for us, what are the monitoring and performance requirements, and then covering some research work, which is part of my patented anode, and the some site trials we have been implemented. So, as we all know, that corrosion of reinforcement is one of the major durability challenge, which leads to rust formation, cracking, falling, dilapidation, and it's costing us up to 3.4% of the world's GDP annually. That's a huge cost. And the major reasons for corrosion in reinforced concrete is due to leakage, dampness, carbonation. In India, particularly, what we are seeing these days is a lot of corrosion is happening in structures due to impurities in the construction water, which has led to severe corrosion in structures, ingress of seawater into concrete, and de-icing salts. So, in general, discussing about the corrosion mechanism. So, as soon as the hydration of cement starts, there's a formation of a passive layer on the steel, which is of gamma Fe2O3. But since concrete is porous in nature, it leads to ingress of chlorides and carbon dioxide, which causes this passive film to break. As a result, anodic site is formed on the steel bar, through which electrons travel and reach the cathodic on the side of the steel bar, which reacts with water and oxygen from the environment and water in the pore water to form hydroxide ions, which again travel to anode and cause formation of ferrous hydroxide, which on subsequent oxidation cause ferric oxide, that is the rust on the anode part of the steel. So if we see a typical circuit diagram of the concrete for this corrosion, so we have a passive steel on in the concrete, and we have an active steel. The potential of the active steel being high, more negative than the passive steel ones. As a result, the corrosion current flows. So all the electrochemical system basically works on Ohm's law, which is simply basically V is equal to IR. Considering the driving voltage is constant, if the resistance is low, that means we have a higher corrosion current. That is the concept behind more corrosion when concrete is low. So in wet structure, the resistance is low, which leads to more corrosion current. Some of the repair methods for protection of corrosion in concrete can be divided into two categories. One is conventional techniques, which covers patch repair, surface coatings, sealers, barriers, and corrosion inhibitors. Whereas the second part, more advanced techniques, are electrochemical techniques, which covers cathodic protection, cathodic prevention, reutilizations, and chloride extractions. In cathodic protection, we again have sacrificial systems and impressed current system. And as per US Federal Highway Administration 2001, CP or cathodic protection is the only rehabilitation technique that has been proven to stop corrosion in soil contaminated districts regardless of chloride content. So today's talk will majorly be focused on impressed current cathodic protection systems. So if we just before moving to the interest current system, we just see the conventional patch repair. What happens is when we have a corroded steel in the concrete, what most of the plant does is they repair this anodic part of the steel by replacing the concrete around it. As a result, what happens is that the old concrete, which still has some chlorides here, becomes the anode, and the new concrete becomes the cathode, which we typically called as a halo effect or the incipient anode effect. So this is some picture which shows this halo effect. If you see around the new concrete, in the old concrete, you could see the corrosion starts to happen again. Same in this picture. So in electrochemical system, what happens? So all electrochemical system basically work on the same principle. We apply an external discrete anode uh, and connect it to the steel bar. It's with an external node. And as a result, the current is passed through the concrete core in terms of an ions towards the steel. And three things are majorly happening. Firstly, chloride, which was around the steel bar causing the corrosion, are repelled against each other. So chloride starts to move away from the steel bar. Secondly, hydroxide ions starts to form on the steel surface. That result that this film which was break down starts to repassivate again. And thirdly, the potential of the anodic site starts to depress. As a result, there is no net current flow between the anode and the cathodic part of the steel bar, and the corrosion starts. So electrochemical systems can treat a large area of structures, not just patch-up corroding areas. There is no problem of incipient anode. It's cheaper and easier than conventional repair in the long term. That means in terms of life cycle costing. But however, it requires some specialist knowledge. And as I said, electrochemical systems can cover electrochemical reutilization, chloride extraction, and cathode protection or prevention. Where reutilization and chloride extraction are basically the temporary techniques, but requires a high current density. And traffic protection and prevention are common techniques, but require much lesser current density. Like for prevention, 1 to 2 milliamperes per meter square, and for protection, about 10 to 20 milliamperes per meter square. So now coming to what is cathodic protection. So as I said, cathodic protection is a corrosion control technique with an application of a direct current onto a metal in case of concrete or reinforcing steel, which as a result, the steel becomes the cathode, and the anode, which is an external anode, delivers the current into the electrolyte. Cathode receives this current from the electrolyte. If you see again this circuit diagram, this is the concrete, and then we apply an external anode. Now, what happens is the anodic current is completely reversed or reduces. As a result, the steel inside the concrete completely becomes the cathode, and the current flows from the external anode to the steel surface inside the concrete. Traffic protection can be divided into two parts, again, based on the application. One is sacrificial systems, one is impressed current systems. And if you see the difference between cathodic protection and prevention, if we see the potential of steel lies somewhere at around less than minus 200 millivolt versus SC when it's not corroded. That means it's in the zone where pitting does not initiate and propagate. When the chloride content increases and the corrosion initiates, what happens is the potential moves to a zone where pitting can both initiate and propagate. So idea behind cathode protection system is to bring down the potentials to more negative potentials, either to zone B or zone C, where fitting does not initiate but can propagate, and zone C, where fitting does not initiate at all and neither propagate, that means passivation is reached. However, in cathode prevention, which is applied to the structures which we know that will face corrosion problems in future, what we generally do is from the onset of the construction of the structures, we apply the system. As a result, we initially bring down the potentials to more negative direction, like somewhere around minus 400 millivolts. So even if the chloride content increases with time, instead of moving to zone A, the stream still moves to zone B. So that's the concept behind cathodic prevention systems. Coming to interest current system, in interest current system, like sacrificial system, we have to apply an external power supply, which is connected to an external anode and to the steel bar. As a result, the current is passed from this anode to the steel, and the chloride ions are repelled against from the steel surface. So the circuit now includes a steel, which is completely cathode, an external anode, the resistance of the concrete, and the resistance of the wire, which are going to the rectifiers. So this table gives us practical CP current density requirements for various steel conditions. So when there is no corrosion happening, steel is concrete is still alkaline in nature, there's low oxygen resupply. So that means the cathode prevention conditions are there. The current density required is about 0.123 or 1 to 2 milliampere per meter square of reinforcement. When concrete is still alkaline, but how the chloride starts to present, the concrete is dry, how the cover is good quality, about 3 to 7 millimeters per meter square of current density is required. However, when the chloride is present in higher quantity, the concrete is typically very poor quality. We need a much higher current density for the protection. Now coming to various anode systems. So the major part of ICCP anode is the anode we choose for the protection, and it depends upon site conditions, what type of anodes are more appropriate, how much design life is required, what is the design current density required, and accordingly we'll choose. So we have mesh and cementitious overlay systems, we have conductive coating systems, we have conductive cementitious overlay, thermally spacing, and MMO coated ribbon anodes, which I will try to discuss briefly in the next few slides. So if we talk about conductive organic coatings, so these coatings are basically solvent-based or water-based binders, which are made electrically conductive by adding some graphite conductive filler to it. So these lightweight, they're thin, generally applied in the range of 400 to 500 micrometer thickness. They're comparatively inexpensive and cover large area. Their current density output is limited, however, we can apply up to 2 to 20 milliampere per meter square of current density per anode surface area. With limited life, the structure can increase up to 15 to 20 years of service life. We can apply a top coat just to protect it from any environmental effects like environmental effects. So any kind of a top coat is suitable for conductive coating systems. It's unsuitable for marine application. It's less durable to the environment. And these coating systems generally fail not because of the graphite content to it, but because of debonding of these paint systems on the concrete substrates. You can see some of these pictures where the defects in the conductive coating anodes and the anode itself has been debonded from the concrete substrate, leading to the failure of the anodes. Next system is conductive cementitious overlay system. These are mainly the straight concrete, which again become electrically conductive by adding nickel-coated carbon fibers to achieve the conductivity. The typical thickness generally is about 8 to 12 mm. However, they have more output than the uh, coating systems, generally more robust, but because the thickness is quite high, it becomes a bit thicker, a bit heavier, and the structure should have sufficient capacity to carry this extra weight. Often there is rough surface finish, impacts profile and clearance of the structure. The requirement of maintenance are however limited. And again, it can increase service life to up to 25 years, but they have to be applied through wet spaces technique system only. Next type of anode we have is thermally spacing. They can be used as again impressed current or galvanic kind of system compared to the conductive coating systems. They are they have longer life. Again, can sustain up to 10 to 25 years of service life, more moisture tolerance, more complex profile. However, they require specialist operators on plants and equipments, which involves high energy and has some health and safety issues in the past for the site operatives. Although they are limited to tidal and splash zones, provided concrete has low resistivity. For this kind of system, the primary anode connector, which is typically used, are either stainless steel or the titanium wires embedded in the process systems. Then we have embeddable anodes. So when we have the structures which are thicker in sections and we want to protect either the bottom reinforcement or the back reinforcement, we have to go for the discrete anode system, which are embeddable inside the concrete. So they're drilled in inside the concrete, so they provide protection at the depth. So the only tricky part is that we have, the missing reinforcement can be sometimes tricky. So they are available in different shapes. Like these are MCM. The first one is typical MMO ribbon. Second is MMO tubular anodes. This one is MMO ribbon uh, rolled into a cylinder. Then we have the ceramic anodes, titanium oxide ceramic anodes, and we have these vent pipes to release the gases in the construction. This is the deck where these multiple of these anodes have been installed. We have to cut down a chase, connect them to the tie wires, the platinum tie wire, and then which goes to the rectifier unit for the connection. Another retaining wall structure where these multiple of these discrete anodes have been installed. So these chase has to be cut for installation of these connector strips. Then we have these ribbon and nodes, again, surface embeddable. So again, cut a chase, small chase on the concrete surface, embed these MMO ribbons. You can hold them in place using these kind of plastic pins. Then in this, the feeder cable is generally titanium strip, which it connects all these ribbons together. And then this goes to the rectifier systems. They have then a cementitious overlay is used to fill this purchase bag. So again, ribbon anodes, they are typically available in range of widths starting from 10 mm, 13 mm, 12.5 mm till 20 mm, and then pass about 2.8 to 5.5 milliampere per linear meter of mesh width, depending on the mesh. These ribbons can also be used for the new construction. Uh, you can tie them if you see somewhere here. We can tie these reinforcement memory ribbons along the steel surface. This can be used for new constructions as well. Then another system we have is mesh and cementitious overlay systems. So like similar to ribbon systems, these systems are in the form of a whole mesh which covers your concrete sections. If you can see this pier column where the whole MMO mesh is being wrapped around the column, and then you can hold them in place using those plastic things. And then this system generally is sprayed. Concrete is used, overlay system is used. Unlike for the discrete anode system, generally the overlay should be carbon-based grout or the cementitious grout, and then get large current outputs from them. So in summary, we have these kind of anodes. We have conductive coating anodes, which typical current density required is about 20 milliampere per meter square, can extend the life to 15 years. However, cannot be used for wet structures or traffic elements. Sprayed concrete, similar current density, can go up to 25 years. MMO mesh with cementitious overlay, a very high amount of current can be passed through it, about 110 to 220 milliampere per meter square. Even the typical anode life is about 120 years. Similarly, for ribbon anodes, discrete anodes, again, much higher life, 50 years of typical anode. Then cementitious overlay with nickel-plated carbon fibers, 20 milliamperes per meter square of concrete surface area. And then typical life is up to 20-25 years. So if we come to the protection criteria, so one part is about the anodes we use. Second part is the protection criteria. So as per BS 12696, 2016, now we have a new code also 2022. So it specifies three protection criteria. So that once the system is energized, we stop the current passing and then we monitor the decay. So if the instantaneous off potential, which is measured generally within 1 second of the switching off the power supply, it's more negative than minus 720 millivolt. Second is if the decay is more than 100 millivolt in 24 hours or more than 150 millivolt in 48 hours. So if we have this on potential when the system was energized, we switch off the system, the current is switched off, we have some initial IR drop, and we reach the instantaneous off potential values. If this instantaneous off potential is more than minus 720 millivolt, the system is working fine. Otherwise, we go for monitor the decay. In 24 hours, if we achieve the 100 millivolt decay, any of these criteria fulfills the protection performance requirement. Recently, NACE published this technical report, TR2146-2020, which specifies the polarization needed depending upon the chloride concentration in concrete. So supposedly if we have a higher chloride content, generally typically for concrete is in the range of zero point 0.8 to 1.6 or even lesser, 100 millivolt is required, which is similar to the protection criteria of BS12696. However, unlike BS criteria, it says that if the chloride concentration is lower, uh, that means zero point 0.6 to 1.2 or even 1.23, even lower polarization can show that system is working fine. In monitoring, we use and we have embeddable reference electrodes for concrete. These reference electrodes are generally two types. One is the true half cell potential electrodes, which are generally for concrete environment is silver chloride electrodes or manganese oxide dioxide electrodes. Other than that, we have some decay probes, the pseudo reference electrodes or inert probes, what we call them. These decay probes are inert electrodes like graphite, MMO-coated titanium, or platinized-coated titanium cannot measure the potential values, but are generally used for measuring the potential difference or the decay criteria. So the advantage of these probes is that have indefinite life, and however, the two half cells can sometimes get damaged. So generally, what is recommended that we use a combination of both true half cell inert probes. So inert probes to measure. So if the CP system is monitored using the 4-hour or 24-hour decay, these inert probes can be used to monitor the decay conditions. And then we also require this TR unit, which is a transformer rectifier unit, which consists of power supplies, the monitoring units, and all those systems. The wiring comes to this TR unit, where the system using this the system is energized. So for an ICCP system, you require those anode systems, you require the reference electrodes for monitoring, and you require this TR unit for energizing the systems. So if we compare them with the sacrificial system, the SCCP system, though simpler installation is there, the design and low maintenance, no external power is required, it's less liable to cause infection, no control system, uh, low risk of hydrogen embrittlement, and cost. However, the cost is not necessarily lower than SCCP system, depending on the geometry. More nodes may be required. However, the disadvantage is we are not able to control current because the SCP system depends upon the potential difference between the steel and the anode. So once installed, we can't control the amount of protection, the degree of protection we have to achieve. And additionally, anodes might require the current demand changes. So they have limited service life. They're not adequate in high resistive environments, has low driving voltage, thus can be used only in less resistive concrete. Not recommended if chloride content is above 1.5% because service life will be significantly shorter. On the other hand, ICCP system have an advantage that we can control current. If in future the conditions changes, we can reduce the amount of protection of the current supplies or increase the current demand as per the requirement. Adequate in high resistive environment, since we are throwing power and current to external power supply, ICP system works even for the highly resistive concrete environment. It has higher lifespan, minimal effect on concrete, and monitoring, we can regularly monitor and show its effectiveness. However, it needs permanent external power supply using the PR unit systems and specialized expertise knowledge is required. Now, coming to the research work, what we did to develop a new anode system, which is called as Concrete Conductive Anode Paint. This contains graphite powders as conductive fillers and solvent-based binder. So these anode systems consist of electrically conductive coatings, and similarly, we use this uh, primary anode conductor as an anomet wire, and its application is used in impressed current systems for reinforced concrete structures. If we see some experimental results, the bond strength is much higher than the carbon-based paints. Uh, Even after exposure, the bond remains above 2 MPa recommended by BS4. We tested it for various anode steel geometries, like starting from small slabs, then to about half a meter beam, then about 3 meters beam, then a full 1 by 1 meter slab with various steel concrete densities, and to figure out how much protection current density can it sustain, how much spacing of this primary and neutral conductor is required, and it's being tested for about 4 to 5 years in the laboratory before finalizing this anode. So if you see that for all these current densities, we are able to achieve the 100 millivolt decay using the MMO inert probes or the decay probes. So in summary, the bond strength is 2.5 MPa. Water is optional. The coating is also acting as a barrier coating, not allowing any external water or chloride to penetrate inside concrete. It has classed as class 1 in terms of water vapor transmission. That means it allows the coating is breathable. It allows the moisture to evaporate from the concrete substrate, the coating substrate, which is generally the reason for the bond failure. Even after bond exposure and passing charge of 50 kilocoulomb per meter square, the bond strength is still very high. Estimated service life, as tested as per NACE standard, is about 30 years. It is within the required current densities. It's suitable for both wet structure and running services and can be easily applied by roller or brush. We have done 2 site trials in UK for this anode. One is in Coventry. We applied this into this bridge pierhead. So we divide the structure into 3 zones. So again, zoning is one of the most important part of CP design. So generally, zone for the zoning part, what we generally do is depending upon the exposures of the structure, the zones are divided. Or in general, the idea is to meet the current density demand, local cathodic current density demand. Typically, zones for impressed current system will have current rating of about zero point 0.5 to 2 amperes, or even we can go up to 5 amperes for the structures which have steel reinforced distribution within the zone is uniform. So as long as this reinforcement within the zone is uniform, we can go even up to 5 amperes of uh, current ratings for the per zone. In this, we use anomite wire in the form of a ring. These anomite wires was then covered with glass fiber tapes to protect it from mechanical damages. And the coating is applied in 2 coats. These are the final installation. The left picture is for the Coventry, where this is the final surface of the conductive coating. These wires gone through these conduit pipes to the junction boxes, and the back end of this, here we have a junction box through which using a multi-core cable, it was going to the TR unit for power supply systems. Another system is this, where we again use this conductive coating system, and we have these conduit cables. Again, you will see that anomite wire was installed using pins to hold them, and then glass fiber tape was used to protect it from mechanical damages, and then the second coat of paint was applied. The monitoring, this is the typical TR unit. If you see, we have 3 zones in this unit, each having its own channel for reference electrodes, for um, negative connection, for positive connection, for test connections. This is the communication box, and through which for the laptop we can set the amount of current we need to pass. We can monitor 4-hour decay, 24-hour decay potential values, the on potential values. The system was initially energized at 20% of the design current density and then monitored according to the baseline. This is how the typical window of this communication board system looks like. So we have the initial potential, we have the instant of potential values, we have the 24-hour and 24-hour decay values. So at last, I think I would like to say that the Western system has been proven worldwide and been used extensively to protect reinforced concrete structures. However, in India, we have to shift the mindset from reactive repairs to proactive protection. It has already been saved thousands of structures worldwide. With growing infrastructure in India and increasing exposure to aggressive environmental conditions, it's time that we bring ICCP into mainstream practice, not just for specialized projects, but as a standard corrosion mitigation tool. Thank you. If you have any questions, I would be happy to answer them. So you can put the question in the Q&A session. So we have a question from Stephen. It says, is the use of remedial CP jet written into Indian highway standards? No, we don't have any Indian standard for CP systems yet, for specifically for concrete structures we talk about. We have the British standard, we have the NACE standard, but no Indian standard yet, neither for sacrificial systems nor for impressive systems. So another question is about cost implications. Thumb rule for per square meter cost. Again, it depends project to project what type of anode we are using. Each anode has its own cost. But if you consider the life cycle cost of the interest current system, it's equivalent. It's much more manageable than the short-term protection systems, like even the coating systems or the inhibitor system or even SACP systems. It's equivalent. The long-term protection we achieve from ICCP systems without need for frequent repairs is equivalent. Even remote monitoring can be used with these TR units, so we don't have to go to the site every time to monitor to record those potential values to see if the protection is achieved or not. The conductive coating systems are much cheaper compared to the MMO ribbons, but the protection achieved by coating systems are lesser compared to the MMO ribbon anodes. Any more questions? This conductive coating system is same as an anode. Yes, the conductive coating is a type of a anode itself. So we have different types of anodes like conductive coatings, MMO ribbons, MMO meshes. We have discrete anodes. So conductive coating is also a kind of an anode for impressed systems. This is RAM connected. If we don't have any more questions, I would like to thank everyone for joining us today. Uh, if you have any questions, you can email to at India Chair. I'll be happy to answer them. Also, if you want to see these certificates, just let us know. So one, we have a few more questions. The British standard is actually an ISO standard. Yes, Paul, that's why. But for the Dalman system, we have been using it. But since ICCP system in India is still not adopted yet, so but we can adopt the DS code for India as well. Conductive coating are similar as thermal sprayed zinc or aluminum. So conductive coatings are generally solvent or water based with uh, graphite fillers into it. Thermally sprayed zinc are a separate kind of anode system which requires some specialist operators and high energy input for installation. But conductive coating can be simply applied by using a spray or a roller. What is the service life for conductive paint anode? So if you're talking about the paint we develop, so generally we claim it to be about 30 years of service life. Once again, thank you everyone for joining us today. Thank you. Okay.